you guys can hear me up the back, I take it. Okay, my name's Riccardo Storti. I'm from Delta Group Engineering, and what we're going to take you through today, hopefully will shed some light on the nature of light. What we're going to cover is the derivation of the mass and size of all existing fundamental particles. We also provide a definition of what size actually is, the Hubble constant, the CMBR temperature, zero-point field, energy properties, and the cosmological evolution process. What I ask people to bear in mind is that we treat all matter as radiators of conjugate photon pairs, in fact, as a spectrum of conjugate photon pairs. And that spectrum can be characterised typically by the highest frequency within that spectrum, because greater than 99.9% of the energy is contained in that spectrum at that top frequency.
All particles?
All fundamental particles, correct. All fundamental particles, correct. Basically here we have the steps that were involved in the derivation process. Probably a lot of it's not familiar to you. Dimensional analysis, Buckingham pi theory, we apply the equivalence principle, we apply Fourier harmonics, we apply the zero-point field theory and the polarizable vacuum model of gravity. Okay, I'm cutting to at this stage a summary of our physical results. Here we have our prediction. EGM is the name that we give our model. It stands for electrogravity magnetics. Here we have experimental measurements. As you can see, if I just draw your attention to the NIST value here at the moment, these two values obviously are not experimental values. They're the official values listed by NIST, but you can see that the error that we get here is really quite small. There has been some fluctuation with error, with respect to error, only a little bit. These calculations are a few years old, but the fluctuation is trivial. It falls well within experimental tolerance. Okay, what's the mathematical pattern responsible? Basically, this value here, that's what I call the harmonic cutoff frequency. Basically, it's the terminating the highest frequency within a spectrum that I described earlier. That's its value here. Basically, we take the ratio of two spectra. We take one particle as our base particle, as our reference particle, and we compare everything relative to that. Okay, this is quite an important table. I'll just draw your attention down here. You can see actual numbers plugged in. Here we've used a proton as our reference particle, and we've got the electron's relationship to it. The text in black is standard model stuff. The stuff in red is what we're actually predicting beyond the standard model. You can see here, for example, with the quarks, you get a very clear pattern: 1, 2, 3, 4, 7, 8, 9, 10. You don't have to be brilliant to figure out that perhaps 5 and 6 might exist in that, and you can apply the same sort of thing to other base particle references. Okay, how do we get our cosmological properties? Look, basically precisely the same way. That equation that you saw before, that ratio relationship, we apply that on a cosmological scale. Effectively, we take the Milky Way galaxy as our reference particle. We call it a galactic reference particle. We shrink it down to a particle. We take the universe, again, shrink it down to a particle, and we basically compare the two properties of the Milky Way that we know against what we don't know in relation to the cosmos, and we're able to determine some very key features. How do we derive the Hubble constant? Well, as I mentioned before, everything to us is photon radiators. We actually define a pair of conjugate photons as being a graviton. We convert that frequency expression that we got before, that I showed you before, into an intensity.
It's conjugate pair of photons as a graviton?
Is what we define as being a graviton. I mean, if you check, I don't want to get sidetracked, but if you check the literature, there is not at all a very clear definition of what a graviton is, and there's many interpretations. We also derive the minimum gravitational lifetime of matter. So what we're able to show is that all matter in the universe has precisely the same gravitational lifetime in a starving situation. So imagine a particle in a universe by itself radiating gravitational energy. That M value there is something that I presented a couple of years ago here, and it turns out that the minimum gravitational lifetime of matter is about 3 trillion years, about 3 trillion times older than the current age of the universe.
Where's that energy coming from?
From the particle itself. Look, I'll get to that. There's a lot to get through, and you'll need to see some other things. How do we get the CMBR temperature? Well, you can see for yourself there, we derive an expansive scaling factor, we derive a thermodynamic scaling factor, we multiply the two, and we get the CMBR temperature. What results did we achieve? Hubble age, 14.6 billion years, Hubble constant, 67.1. I just point out it's within 5.5% of the community agreed sort of average value, but that's very, very rough. We get a result, the temperature result within 0.01% of the very precisely measured WMAP value. We're also able to simultaneously derive, or rather improve upon galactic radii calculations and total mass calculations. What do the results demonstrate? Well, one, that we believe that, the influence of dark matter and energy upon the Hubble constant is less than 1%. That's completely contrary to standard cosmology, but we believe we can back that up with numbers. The universe is greater than 95% photons, less than 1% dark matter, and typical 4% atoms. We also believe we've calculated that the average cosmological value of zero-point field energy is extremely small, 10 to the minus 13, meaning that there is really no practical extraction of energy from the zero-point field possible at all.
But is that result in conflict with the general view that dark matter is...
Correct, yes it is. Yes it is. Okay, what's the mathematical key? Look, here's our particle physics representation, an equation about an inch long that you can generate the mass and size of all fundamental particles from that equation. That literally does transform directly into a temperature relationship incorporating the Hubble constant. These constants here are all forwardly derived, none of them back calculated to sort of make everything fit. It's all one derivation process going forward. These things come out. This, I don't have a name for this, but this here is the Hubble constant at the instant of the Big Bang that we calculate. Okay, look, R1 and R2 is just two different particles. You choose one to be a reference particle, one to be what you're interested in, and the same with mass. So, no, sorry, it's their physical radii, the physical dimensions of the particle. So it's not their position in space, but their physical dimensions.
And M1 and M2 is their
mass, correct, yeah. Okay, here we have the temperature curve that comes out. This was quite a shock to me. I did not expect to get this curve at all. It looks very Planckish, very blackbody radiation. We did not use the blackbody radiation law at all. So I was surprised as anybody to see this. We started off from time t equals 0. In fact, that axis is labelled incorrectly. But we started off from time t equals 0. We actually calculated a value of 0 Kelvin at the instant of the Big Bang, which is exactly what you'd expect. For example, a supermassive black hole should have a theoretical temperature of 0. So, sorry, now that H alpha value is roughly equal to 0.37 times the Planck frequency. Here we have, I'll race through this, just derivatives of those curves. They all have exact solutions, by the way, and key features have been illustrated, local maxima, minima, etc. Okay, this is the gradient curve of the Hubble constant, very important. You can see here that we're able to actually overlay information and get it from these curves. Cosmological inflation becomes clearly defined, expansion becomes clearly defined, and key points there, temperature points, also drop out. You'll see that, this shows that the gradient of the Hubble constant is positive currently, which is not at all determined by the standard model. It was in fact a big surprise, but that just drops straight out with no fuss at all. Again, second derivative curves, I might even have a third, no. Here we go, I've taken, this is just a magnitude of the previous gradient curve that I showed. The reason for this is that it physically, because the values are so large and they can be so negative, it just physically fits onto the screen, onto the page there neatly, so I took the magnitude. With overlay information as well, we're able to actually carve up in precise mathematical terms distinct periods in the cosmological evolution process. Primordial inflation, that's before the Big Bang. Thermal inflation from the Big Bang to the point of maximum thermal temperature. Hubble, what I call Hubble inflation, and then Hubble expansion. This is the standard Big Bang model. All the temperature calculations that we get agree perfectly with this, absolutely perfectly. In fact, the standard model itself implies that if you look at this end here, you'll see particles and photons being represented. I take that to be the wave-particle duality, and I interpret that to mean that the standard model actually says that all matter is really made up of photons. More on that in a moment. Summary points with quasi-unified particle physics. Now I call this a method, it's not a theory, because it can have different interpretations. We also derive the Casimir force. I did that a couple of years ago. And we've derived two of the most important cosmological parameters and made new predictions. So what does all this mean? That the gravitational spectrum is a simple but extreme extension of the EM spectrum. There may be as many as 5+ undiscovered particles. The Hubble constant and CMBR temperature are in fact related. I believe matter is just a condensed form of photons, and a photon is a propagating piece of matter, and I hope you're impressed by that wonderful effect there. That's it, finished, done. Thanks a lot, I appreciate your time.